giving me the opportunity to talk about our results here. And well, you might see that well, our institute is also doing lots of quantum mechanics, and there is also this kind of superposition state where in the program there was this nice Chloe A coming in, and I just normally will be written this way, just to avoid any confusion here. But in this regard, I need to first thank, of course, all the people that contributed to the work that I'll be showing to you. There is, of course, 2 PhD students here, Janine Gückelhorn and Tobias Wimmer, who did a lot of the experimental work that I will be showing to you. And a big thank you goes also out to Akash. He was the one that helped us a lot in understanding the theory behind what I will be telling you today about the Magnon-Hanle effect. And in our world of spintronics, I would say we're currently all using the effects that have been discussed for quite a while by Albert Feld about the giant magnetoresistance effect and tunneling magnetoresistance state. And we have these 2 spin states of the electrons that we use to get to these effects. But of course, development has been going on. And using these electron spin states, there have been several proposals coming up to use for new applications. So on the one hand side, we were talking a lot about spin transfer, spin orbit torque effects, where you can use that either to manipulate information, so using that to store information, or you can even use that to excite magnetization dynamics and use that for gigahertz applications or even going to terahertz. On the other hand, of course, there's a lot of discussion going on about surface states, spin polarized surface states that you could use for more efficient spin orbit torques or even more exciting new fields where you might use these surface charge currents. On the other hand, I mean, this is one of the proposals, the spin transistor, that has been around for quite a while by Dadadas proposed, where the idea was that here in this channel, when you inject spins, you rotate them by a gate-controllable spin-orbit coupling such that they can rotate and you can really reverse the orientation. And of course, currently all of the experiments that have been done in this direction show that there is some way of manipulating spin-orbit coupling, but the effect is so weak that it will not work for device applications. Still, this rotation that you can do with the spin is useful in the experiments, especially if you want to prove that the effect that you measured is coming from the electron spin and not some artificial effect due to your structure here. So here I showed an example for the electronic Hanle effect, where what you do is this lateral spin wave structure. You have 2 ferromagnets, here made out of cobalt. You pass a current here through that arm here. You have a connection with the aluminum layer. And then here at this point, you have spin injection into the aluminum and a diffusive spin current also going to the second cobalt electrode, and you can measure then a voltage drop over here. So that's typically happening in the system. And now you can, of course, start to apply an external magnetic field to get a precession of that electron spin while it propagates in this aluminum channel. And in this way, you will change the orientation that arrives at the cobalt detector, and depending if it's parallel or anti-parallel, you can really switch the voltage that you detect there. And this has been pioneered by the work by Bart van Wees first in this metallic systems, where you can really show then, okay, I crank up the magnetic field and get these oscillations nicely going on. Of course, you can also go to more suitable materials where you can see more of these oscillations, where lots of experiments has been done with semiconducting materials, where you can go to a ballistic spin transport regime, and you see lots of these oscillations. Now, my perspective, or the perspective also here that we discussed a lot about, were also Magnon systems. So I just repeat a couple of key things because there has been so much discussion already going on in this regard, but I think the most important thing in regards to antiferromagnets is, now if you take a uniaxial antiferromagnet, we have these 2 Magnon modes that have different circular polarizations. So we have left and right circularly polarized Magnon modes. Speaking again in the language of spin states, you can also envision them as kind of having a spin up and a spin down Magnon in that system. And then in these typical experiments that have been discussed about pure spin and pure charge currents, you can also envision a pure Magnon current where you have just the same number of spin up and spin down Magnons are moving in the same direction, or you have a pure spin current in the system where now the Magnons need to move in opposite directions in the system. And in most cases, what you have with these 2 different Magnon modes, that are in the system, they are completely degenerate that we have. Now, for the experiments, what we need is a control way or an access to these Magnon modes, and what I'll be using are, in the end, spin-to-charge conversion using the electron system. So you heard about the spin Hall effect in these systems. So this allows me to change a charge current into a spin current and then use kind of this transversal geometry to inject spin currents into adjacent materials if I take a heavy metal. And I can also use the inverse effect to get that as a way of having a charge detection. So if I get a spin current into the heavy metal, then I will detect it via a charge current in the system. And this leads to the technique that I coined the all-electrical Magnontransport experiments. And here what you use is now you bring this heavy metal, in most cases it will be platinum, in contact with a magnetically ordered insulator. It can be either a ferro, or an antiferromagnet, or even something with more complex order. And now the key thing here is that in this magnetically ordered insulator, at finite temperatures, you have a thermal Magnon gas. And with this, you can interact now. So if you drive a charge current here, you will generate a spin accumulation in the normal metal at the interface. And if now the order parameter is collinear with that, you can access this magnonic system and can either now increase the number of magnons, now in case for an antiferromagnet for a specific mode, so either the left or the right circularly polarized mode. And if you then look into the other Magnon mode, you can kind of pull out thermal magnons of the system, reduce the number of magnons in the system. So this would be either kind of generation or absorption happening at the interface. And of course, if you flip kind of this orientation between this spin direction and the end, it's just the other way around. One mode gets then populated and the other not. And you can now use that to build up devices to study this effect. So what you do is you have kind of two normal metal strips on top of this magnetically ordered insulator. This is always in the dimensions of nanometer, several hundred nanometers in this way, so separation, couple of hundred nanometers, maybe even microns. And now you drive a charge current through the system over here, generate your spin accumulation. This will generate a Magnon accumulation, and the magnons will then diffusively fade out in this magnetically ordered insulator, also reaching that detector over there, where you can now use the spin current arriving here to be detected as a voltage drop due to, again, to the inverse spin Hall effect that we have in the system. And there's lots of work going on. This is also not a complete list here, but I think there were two important results. First of all, of course, the real experimental demonstration that it actually works, these processes. This has been done by the Bart van Wees group back in 2015, where they used yttrium iron garnet and can really show that there is a Magnon current that is transported in the system. And later on, importantly, to go over to antiferromagnets, and a group by Matthias, they could show also that in hematite, you can really detect the Magnon current in the system using the same injection and detection scheme that I have been introducing to you. And now one of the things when you think about the antiferromagnetic part now, with these two Magnon modes, you can make this very simple thing again, saying, okay, we have these two spin states, spin up, spin down. In this case, when I do this injection experiment, there will be an accumulation for the one Magnon mode. This will diffuse over in this direction, and there will be depletion on this side, so magnons will diffuse in the other direction. So speaking again in my naive picture of a pure spin current, this is exactly what's happening over there. But of course, there can be also some effects where these two modes couple with each other, and I can transform now from spin up to spin down magnons. And one of the key things that we try to analyze now is figuring out how can we describe that? How is it possible to get a good description? And this is where Akash comes in. And he was proposing a very interesting property, or pseudospin, he termed that term, and this reflects kind of the polarization state that we are in the Magnon system. So in the picture here now, reminding us of a Bloch sphere in the end, we have kind of the Z component of the pseudospin, And this reflects, if it's kind of in the positive Z direction, you get a right circular Magnon mode, and if it's in the negative Z direction, the pseudospin, you have the left circular polarized Magnon modes. Of course, you still have kind of these X direction and the Y direction, and here you have kind of the superpositions now of these two circular polarized modes. So you can either have a linear polarized mode lying in this plane or in that plane, and of course also along the Y direction you would also have some superposition states of these circular polarized modes. So the nice thing is that with this mapping onto the pseudospin, we can very easily describe now also these coupling effects when it transitions from right to left circular and back very easily. And indeed, one then needs to motivate what's going on here. So to get these pseudospin, of course, to precess now, so changing its way, you need to have a so-called pseudo field acting on the system, which comes from the mode coupling that we have in the system. So from the theory side, now the question is, where does this mode coupling come from? And if you think about this, it's just coming from the fact that you need to have a breaking of the rotational symmetry about the Néel vector. And this comes, in the end, from systems where you have going over from a uniaxial anisotropy to an easy plane anisotropy in the system. So then, indeed, you get a coupling between these two modes in the system. And then what you need to do, if you have this description of the mode coupling, you can go over and write down now a diffusive pseudospin transport equation where the important things is now that this is really a density then in the end that we need to describe. So it's an ensemble of magnons that is propagating in the system. And the first term that you see over here, that's kind of the typical diffusive transport for spins, where you always have a certain spin lifetime in the system and a diffusive constant. And the second term that we have here in addition, that's something, well, guys doing spin transport and electronic spin Hanle effect might recognize. It's a very similar precession term that we have now, indicating that the pseudospin will precess around this omega coupling that looks like a magnetic field applied in the Y direction for the pseudospin pseudofield. And indeed, what you can think about then, if you do this kind of propagation now of this Magnon ensemble, then your pseudospin first, you do the injection. So that's the nice thing about the electrical injection that we do, that we can indeed determine by the charge current direction the spin orientation here, and this will be the same for the pseudospin. And then you let it propagate in the system. You have a time evolution due to that mode coupling, the pseudo field that is over there, and then the pseudospin will precess, and depending how long it will take the magnon to propagate in the system, you can really then fully revert it, get a negative or spin down magnon in the system, so transitioning from right circular to left circular, or you can also end up in a spin zero state in the system. So it's easy to control that. And one of the issues is, of course, in the experiment now you want to have access to that mode coupling omega. So what system did we use for these experiments? So it's the one that you have been also shown quite a lot now. That's the Hematite. Again, as Andy also rightly pointed out, there is a net magnetic moment that we can easily use in the experiment to orient the Néel order parameter. And that's exactly what we're doing. So we apply the external magnetic field now parallel to this injector strips and detector strips, such that the Néel order parameter will be again perpendicular oriented, and in this way collinear to the spin direction in the experiments. Another thing I need to mention now in our experiments, we have rather thin hematite layers. They show no Moran transition. So in all the temperatures that we investigated, we always see the easy plane phase of the system. So spins aligned or magnetic moments aligned in the C plane of the system, and we use a C-axis oriented sample. Now, with knowing the magnetic system that we are looking into, one can also have a look into this mode coupling and what is determining this mode coupling. So I already talked about an easy plane anisotropy that is important, but the interesting thing is now, due to that canting that we also have in the hematite layer, we have an additional contribution that determines the mode coupling. And interestingly, there's this minus sign in between. And with an external magnetic field, we have also access to the canting angle, so we can tune this second contribution here. And this means we have a full external control over this mode coupling in our experiments. Then, of course, you can solve the diffusion equation using some boundary conditions. We have some discussion also in our publications about what are suitable boundary conditions, but here you just assume that you inject at one point, and you use, of course, a 1D diffusion equation, and you assume that in infinity this spin current then fades out into the system. And then you can come up with the steady state solution. Don't be too shocked with all of these different equations that are over there. On the next slide, I will show you how it actually looks like in the experiment, and this, especially the magnetic field dependence that is hidden in this omega term over here. So this is now one of the typical experiments. Data points shown here now for different separations between the platinum electrodes that we use in these experiments. And one sees several interesting features. I would say we first focus here on this maximum that we see at around 8 Tesla of applied external magnetic field. And that's exactly the point where in this contribution here, the mode coupling is switched off now. The easy plane anisotropy contribution and this Canting contribution just cancel each other, and so there's no pseudospin precession happening at all in the transport. And in this way, we just inject spins, they propagate through the system, and we detect them. So that's happening here at that point. And of course, due to that, its intrinsic properties, the maximum is exactly at the same position for these two different distances. Things change now if we go away with the magnetic field from this compensation field. So for example, here in the black data points, you see that we can go from a positive signal to 0 at this position here. And what exactly happens here is now, okay, we go away from the compensated situation where mode coupling is switched off, and now we allow for that mode coupling to be finite, and we get to the position where now when the magnons propagate, we get into a spin 0 state, which we can't detect with our platinum detector anymore, and that's the reason why the signal goes to 0. But you can go even further, and then the signal reverts itself, and then it comes back a little bit to the positive side, and then it dies out due to the finite spin lifetime of our magnons in the system. And the white lines that are shown here in this graph, that's exactly the theory equations that I have been showing before you. So we can extract then from this some information about the compensation field and also on the spin lifetime from these graphs over there. So the nice thing that also comes out in this description here is that indeed now we are able, when we go to this inversion field, to really change the spin orientation that we injected to the opposite side. So that's a very interesting thing, reminding one again of the proposed spin transistor of NMR. And the other thing that we can also compare now to is, of course, the electronic Hanle effect, which is very similar. Just here it's the electron spin, and here's the pseudospin component. There's one of the huge differences, of course. Here, if we apply the field perpendicular to the spin direction, we start at 0 field, getting the maximum, and then it dies out. Here, we need to first, due to the intrinsic properties of the material, go to a finite field to completely switch off this precession. And what we can now do a little bit more in detail is now figuring out several details of that properties of this Magnon-Hanle effect. And I think one of the critical things is also thinking about dimensionality in the systems. And for this, you can think about, of course, what is a transition when you go from a 3D Magnon system to a 2D system. And I think if you look into the thermal Magnon wavelength, that tells you what kind of feature sizes you want to achieve. If you look into these properties for at room temperature, you come up with 3 nanometers for hematite and also for yttrium iron garnet. So this means we would need very small structures to be able to go into this regime. Nevertheless, the Bart van Wees group now has done some very intriguing experiments in yttrium iron garnet, which I wanted to briefly advertise here, where they went down with the thickness of the yttrium iron garnet layer to very low values, and they could extract still very sizable signals in the detectors, which shows in the end that some surface scattering effects that you might think about coming into play when you make the thickness very small are not a problem in the yttrium iron garnet. I mean, I would not say it's completely understood why that's the case, but it's very intriguing to see. And if you then do some calculations, you can even show that the spin conductivity in such a thin yttrium iron garnet layer is comparable to copper, for example, or even graphene if you try to do the transition to 2D materials. In our case, of course, there's one of the questions. We have used a 1D diffusion equation, and of course, this is only the reason that we get some analytical results. If you go to 2D, it's no longer possible. And this means we should be with the thickness lower than this decay length of the magnons in the system, such that the 1D approximation is reasonable. So we try to change the thickness now of the hematite layers, and looking more into that. There's one important thing that I did not mention to you. So the hematite is in the easy plane configuration, so normally you would also have linear polarized modes. Just due to the platinum injection, we can really do then a superposition of these two linear polarized modes, getting circular polarized magnons out of it. But if you look very closely, so in the beginning I was showing you and saying, okay, these two modes are degenerate, but exactly if you go to very small K values, you see that these two modes will split up. And one of the things that also Romain was already explaining nicely is that at these low K values, or K equals 0, when you drive them now with a microwave field, you have some finite ellipticity in the system, so you have angular momentum that can also be transported by these magnons. Nice thing is that you can gap out or remove that gap with the external magnetic field, so you can again get with a finite magnetic field to a state where the magnon modes are again degenerate, or even at higher magnetic fields you reverse the situation in the system. And as shown over there, they have several groups now showing that indeed you can detect some spin pumping with this low K magnons. So why is that not a problem in the first experiment that I have been showing to you, that we have these contributions? So one of the reasons is really the thickness that we have of these magnon modes, and they allow us to effectively gap out these low K magnons in the systems. Of course, if we go to higher thickness values, we should get then some finite contributions from these magnon modes, and this is exactly what we set out to do. And there are some results now, so a comparison here. This is a new sample with 50 nanometers and another sample grown in the same run with 100 nanometers. And you see that it's very distinctively different, the results that we get. So here again, you see this nice Hanle curve shape that we can fit also with the data. On the right-hand side, the only thing that we see here is kind of a contribution where we have a hump. That hump we identify again as this compensation field. That is a signature that comes from the high K magnons that we have in the system, but there's kind of this plateau that we see here. So it starts to saturate first and then remains very constant and then goes into this hump region, which we identify with a contribution from the low energy magnons that have finite spin, and they will contribute. And if you go to high enough magnetic fields, they will decay and fade out. There's another feature where we are still unsure where it's coming from. So if anybody has a good idea what it is, I will be happy to discuss. We see some oscillations happening here at very high magnetic fields in the signal. It's really a signal that's coming from the sample. We did lots of control experiments and also can show that this contribution has some temperature dependence. But as said, currently we have no real clue what is really causing and why it's there. It's mostly that we see it in very thick layers. In the thinner layers, these oscillations are less to be seen or not at all to be seen. And of course, you can then extract the temperature dependence of this compensation field also for the thin films, for different distances and all of that. You see, again, very nice agreement between these two, and it also follows the typical anisotropy dependence that one would expect for hematite in the system. Since I thought that it might be a good thing for starting the discussion, I also wanted to bring to attention some of the open challenges, open tasks that I would see in this field here that I try to introduce to you. Of course, there's still kind of the, I would say one of the issues, figuring out this idea of having a temperature gradient generating a transverse spin magnon current and getting some experimental evidence really that this effect exists. There's lots of theory behind that saying, okay, we need to see that. Also some proposals going into the direction of Magnon topological insulators. So as said previously, we can do that now also with magnons when we've just used that what the electron spin is already doing. So there should be some surface states. But still this question would be, how can we detect such surface states easily in the experiment? So with the platinum structures that I showed to you, there's no way of doing that at all. So we need to be more clever in doing this kind of effect. I think also, from my perspective, of course, for this Magnon-Hanle effect, it would be nice to have a way of having a coherent excitation scheme that allows us to selectively select a superposition state now of this two linear polarized Magnon modes being circularly polarized, and let that propagate with a certain k-vector and see if this Hanle effect is also there in these systems. From the theoretical description, it should be. And I think then one of the interesting things would be also talking about now, as already has been pointed out by the keynote talk today, what are magnonic properties of these altermagnets, and can they lead to also some interesting Magnon spin bands in these structures and all so forth. And one thing we are currently thinking about is kind of spin orbit effects, emerging spin orbit effects in this Magnon-Hanle effect. And in the electronic case, there's, of course, lots of work been done with 2D electron gases, where you have then in addition spin orbit contributions that really lead to a precession of the injected spins, if that is kind of perpendicular to the spin orbit field at that given k point. You can really show then that this leads to a precession. This would be something interesting to also observe, of course, in the magnonic case of that effect. And with that, I come to the summary and conclusion. First of all, just showing you that indeed you can have this Magnon-Hanle effect in an antiferromagnetic insulator, giving you a tool at hand to probe this Magnon-Transport and really also show kind of this two-valuedness of Magnons in the antiferromagnetic insulator, having spin up and spin down Magnons in the system. And of course, there's still lots of things to understand, like these oscillations. So it's an open field, and I encourage everybody that is interested in that to start studying it. So with that, I thank you for your attention.
Thank you very much. Questions?